What it will be is pretty much you'll do the design. I'll give you some guidelines so you can find the calculations pretty much directly in the book. You'll do some calculations, show me your calculations. You'll have to find the resistors and capacitors. You can get those at the EPL. They're pretty cheap, and if you have trouble finding them, let me know. I have a ton of extra through-hole capacitors and resistors if you need them. I'll give you a general guideline, and then pretty much what you'll be doing there, once you have your design, is you'll be taking your steady state measurements again and your load switching measurements and reporting on that, and that should be it. It'll still be due Friday of finals week, but it'll be a very reduced, and I'll have you do probably a table too, making comparisons and probably a question or two, but I'm going to severely reduce that from its current state. Courses right now, I'm hoping to get at least through lecture 14, maybe a little bit into 15. I'm going to start this over because like I said, last Wednesday I was very off and I didn't like how I was going through that. So I'm going to start over on lecture 14, hopefully get a little bit into 15, finish up 15. I'd like to get into steady state error, lecture 16, but I don't think I'm going to have the time to get to that. That's actually a very long 40 slide lecture, which is, it's interesting stuff. I wish I would have tried to get that in earlier, but I don't think I'll be able to cover that. I will get you guys a practice midterm by tomorrow night at the latest, and you'll have until the start of class next Wednesday, because I want to dedicate Wednesday to review. Do you have a question?
Yeah. So the final, this is still going to be like 40% of the grade?
It is still going to be 40% of your grade, yes. So yes, it is very important. I'm learning a lot from this semester. I tried to keep it with Dr. Tymersky's setup because I am new to teaching. Also, if you guys might have seen the emails, the professor reviews are open. Please review me honestly. I don't even know if I assume it's all anonymous, but I would like an honest review to help me. It doesn't sound like they're going to have me come back in the fall anyways, but I might like to come back to teaching later on in my career, so I appreciate the feedback, and please be honest. Let's see. Covered that. Midterm, practice final, I'll have posted tonight. The final, because we did not get a lot of new material, most of it will be focused on some of the earlier stuff, so stuff we had up until the midterm. So it should be, if you've reviewed your midterm and feel confident in that, you should have some very familiar questions on there. I haven't written the final yet, but I already have a few ideas for some of the newer stuff. I won't be having you draw Bodie plots. I'll be providing you with the Dr. Tymersky's Bodie plot summary on the final, so you don't need to take time up on your cheat sheet to put all this information on there. It'll be on there. Most of this will be recognizing I'll give you Bodie plots and you'll need to plug in some values, probably not calculate them, but at least recognize them. Just to give you a heads up on that. Let's see here. Let's see. I mentioned the lab is currently due Monday. I'm going to push a late entry till Wednesday. I know I looked over 7 out of 9 of the initial submissions, and looks like I made a few comments, things that a couple needed to probably check on. I haven't checked on the other 2. I know at least one other group was still having trouble with their build. I didn't check on the final group, but I'll look into that, make sure I sign off on that tonight and give you any feedback. I did release I did also, my computer, I have lost all the information on my laptop at this point, so I had to grade those from memory. That was very lenient, I believe, so as long as you were at least on the right track, you got most of the points. I'll obviously have to do the same with this one, but lab 4, 5, well, my lab 4, I'm much more familiar with. I will make the comment, I put in a few things about some of your MATLAB code that seem to have issues. Make sure you make those corrections for your current MATLAB code that'll be due for Lab 4. I wanted to make sure I got that in. I was hoping to recover my data, but at this point I might have lost a lot there, which sucks. Let's see, that covers that. I'm not gonna go over the homework. I'm gonna try and get that posted for you guys tonight. If you have questions on that, please feel free to reach out to me. I know a few people will reach out to me about question 3. That was very poorly worded, I think. So if I do anything similar to that on the final, I will fix some of my wording there. Let's see. Any questions so far on anything I just kind of brought up? No? Everybody feeling pretty confident about finishing up Lab 4 at this point, for the most part?
It's just reduced, right? Lab 4.
Lab 4 is definitely, it is reduced from what is in the book. I did reference the MATLAB directly from the book. I didn't include that, but please refer to the PDF of the book for the MATLAB requirements. I at least explicitly said which ones to do. Let's see. So yeah, so most of your work at this point for Lab 4 will be MATLAB and one more PEC simulation, answering a few questions, and then possibly going back and remeasuring a few things on your circuit just to make sure you have your values down right. But as long as your circuit is working properly, it should be mostly focusing on the simulations for MATLAB and answering MATLAB PECs and answering a few questions. So it shouldn't be too bad. I still feel like the time crunch is a little much, so I apologize for that, but we didn't get the board still about 2 weeks ago. Okay, let me try and, any other questions before I get started here? Okay.
Are we going over the homework?
I just said, I'm not gonna go over it because we're low on time, but I will post the answers after class. I didn't remember to print it out, but I will get that posted after my office hours and after I get home and get it all put up. But if you have questions after, feel free to email me on anything you're confused about. Okay. So, getting back to Bodie plot and using that for compensation. I think I was just trying to rush through too much last week, so that's why I'm gonna refresh on a bunch of this. So just in review, we have some advantages to using the Bodie plots. We can easily, relatively quickly, sketch these out using some straight line approximations. The gain margin, phase margin, crossover frequencies can be determined from that Bodie plot approximations. And then from there, our controller design is relatively simple. You have to understand a few things, but once you're looking at your actual Bodie plot, you can kind of see where you have deficiencies and where you might need to make some improvements. So we're gonna cover 5 different types of compensators. I know this lead with integrator and zero compensator is pretty much what you'll be designing for Lab 6. Like I said, I will direct you guys to some of the pages in Dr. Ty Murphy's book that will greatly help you there and offer a few very helpful hints that will make your design easier to find components for. So, looking at our lab here, we have our loop gain here, which is described by using these main gain blocks. So we have our compensator that we'll be designing for, pulse width modulator, it's pretty set there. We have our plant, and then we have the sensor gain. This is all compiled here in the form of T of S, which we have 1/VM, gain of the compensator, GBD, and the sensor. We call it the plant itself. So we have our uncompensated system. we have GBD equals VG over our, word for it again, second order system. So we have a Q factor, we have a natural frequency, and we're assuming here that our compensator in this uncompensated system is just 1. So loop gain, we're referencing T0. We're kind of putting all those gain values into one constant here. And for this example, we're going to be saying that T0 is 2.33. We're using a Q value of 9.5 with a natural frequency in hertz of 1 kilohertz. So now we have our uncompensated system here drawn out using the Bode plots. So we have our natural frequency of about 1 kilohertz. We have the gain, you'd say, of 2.33, the T0. And then we have our crossover frequency here at about 1.5 kilohertz. And this is, you can already see right here, with that crossover at 1.5 kilohertz, we're already at negative 180 degrees. So we need some compensation to get the phase margin brought up. That's about all I need to cover on this. So here, using the lead compensator, this is just the Bode plot of this lead compensator. So we have the flat gain of GC0 compensator, and then we have an increase of 20 dB per decade right around F of Z, and at F of P, so we have our F of Z, F of P. We want to make sure our omega Z frequency is less than omega P in this case. So the numerator has to have a smaller natural frequency than the denominator. Doing so, we have the gain going up to about that F of P and then flattening out. And what happens here for our phase is we get a nice phase bump going on here. So we're increasing 45 degrees per decade from F of Z over 10 to F of P over 10. And we have a flat response in our phase between F of P over 10 and 10 F of Z. You can see that. Increase it a little bit more. There we go. So these are kind of our main points for the frequency. And you can see this is in between our F of Z and F of P. Then we decrease back down and return to our 0 degree response after 10 F of P. Questions on that so far? Make sure these are clear. So this is, again, just the lead compensation. So we're kind of designing, at this point, we're looking at just one part of what we need to fix in our uncompensated system. We know we need a phase boost. To accomplish this phase boost, we'll have the lead compensator. Oh, and I think this is actually getting into it. The basic idea is, again, we want to add that phase boost at our unity crossover frequency. So we'll extend the bandwidth, unity gain crossover frequency, while also providing that phase boost. The maximum phase boost occurs at the frequency of the square root of F of Z, F of P. So we want to set our new crossover frequency at that square root of F of Z, F of P. So here, again, we're using, this is the transfer function given previously. The lead compensated loop gain here would be our uncompensated system times the compensation. So that gives us our T of C here. So looking at this across here, kind of just compiling everything. If there's any more to actually explain on that, just multiplying these two out because these two loop gains multiply together. So now combining those two on the Bode plot, we have, I'll get into the phase boost in just a bit. But
So we're trying to get that phase margin between 45 and 60?
optimally, yes.
Is that 0 in this case?
Previously, if we look at it back here, this is what we're looking at here, and we're already at minus 180 degrees, so
So it becomes 0?
it is 0 phase margin. We have no phase margin at this point. Adding the lead compensation provides us this slight phase boost at this specific new corner frequency, or cutoff frequency. Crossover, jeez, all the C's. But here, we've taken the Bode plot of the original, I guess you can call it T0 of S, and combine it with the lead compensator. So now we're seeing our new gain, flat gain at low frequencies is T0 times G C0. We then still decrease, but here you can see that the gain, because of this, and I'll go back to it, the slight boost that we have in this frequency range, we kind of start to level out for the magnitude gain here. And then once we've hit that F of P, we're back to reducing by negative 40 dBs per decibel, which is good because we want to have noise reduction at the end. Here, then this is the main thing that we're looking at here with the phase boost that we're trying to accomplish. So we have here, we still have the 0 degrees until we hit about, I believe this is F of Z over 10. We start to have a slight phase boost increase before our actual F of 0. But then it rapidly decreases and we still have this slight phase increase. I guess, I wish I had these side by side. It would be so much easier to kind of show the comparison. But you can see this, because of that lead compensator, we still have this phase boost going on here at F of 0. We're still having the severe decrease down to where we hit minus 180. But then this F of Z over 10 to F of Z, still slightly increasing there. But it's dominated for a little while by that, because it's second order system, negative Q times 180 minus 45 degrees per decade. And evens out here. But now we have that flat response in the phase, right about where our new crossover frequency is. And then we again decrease until we hit about minus 180 here. So what we've accomplished, and I think, yep, geez, should be more familiar. When we blow this up, you can kind of see a little bit more. Our phase margin here is about 45 degrees. Because if we take, I guess this is getting into it too. When we design this, we're also designing for F of P and F of Z, where we want F of Z to be, F of P to be 10 times F of Z. This way, when we are actually in this phase flattening area, or where we've added our phase boost, we have a 45 log of 10 over 1, which gives us 45 degrees. Does that make sense? Everybody following along so far?
So we're kind of sacrificing some attenuation for phase stability?
Yes. So pretty much, yeah.
Is that going to be an issue for certain things that we actually want to attenuate? 'Cause
Possibly. It depends on how dedicated we are to some of the noise reduction that would be going on in these higher frequencies.
Because we're losing some of the benefit of that second order.
Yes,
Right.
but only for like a small frequency range, I guess, relative to what we're looking at.
Okay.
It really depends on, the main thing here is we want that phase boost because we want the stability. But we will sacrifice a little bit of noise reduction at these higher frequencies. But because we're only decreasing that attenuation in a certain frequency range, I think that's, depending on the design you're going for, you might be able to allow that. For us right now, doing this actual lab, we can tolerate some noise in our system there. And this will, this is gonna be an iterative process right now, so we're going through just the lead compensator, but as you see when we go through some of the other compensators, we're kind of combining the different ideas, and you'll see some of these change. I guess, we'll be changing certain areas of the Bodie plot. Right now, we're just focusing on the phase margin. And here again, we got this blown up, but also explaining that we want, at least for this, because we're looking for 45-degree phase margin, we're making F of P to F of Z 10 times the other. We could sacrifice a little bit of that phase margin by reducing those F of P and F of Z, but if we're aiming for 45 degrees in our straight line approximations, again, these are approximations, we'll see how the actual system responds, but we would like about 45 degrees. But like I said, if we brought F of P and F of Z closer together, we would end up with less phase margin, but if we wanted to spread it out even further, we could sacrifice more noise reduction, then we could actually increase that to larger values. But if we're aiming for that 45 degrees in our design, F of P equals 10 Z. It's a good question, thank you. Here, we also want to set the unity gain to our new crossover frequency. So if we're doing, using the 45-degree phase margin, we're gonna say let F of C equal 5 kilohertz here, someplace out beyond our F of 0. Then we have this, and I don't want to get into it too much, but because it's logarithmic, we're using the square root values here rather than a arithmetic mean? Geometric mean, thank you. So we have to use the square root instead of 1 plus the other divided by 2. Just a little bit.
That is the geometric.
Right, is that then not what I was, yeah, what I was getting at, yeah. Oh,
Arithmetic.
it sounds weird, but I think that's right. Written, I'm seeing the word. The arithmetic mean is the averaging of two values. That would be 1 plus 1 divided by 2, so our average is a half. But we're looking at logarithmic scale here on our Bodie plot, so we want to use the geometric mean thing. So here, F of Z would be 5 kilohertz over the square root of 10, which gives us 1.58 kilohertz. And knowing that F of P is 10 times that, we have the F of P at 15.8 kilohertz. Making sense so far? While we're choosing some of these values, the 5 kilohertz was kind of a choice there. But everything else should make sense. Again, we're combining here because we know F of Z is 10 times F of P. We can simplify this down to F of Z squared times 10. We set 5 kilohertz as our new crossover, giving us actually calculating out our F of Z and F of P. So we have found our omega Z and omega P. Obviously, just remember we have using frequency. We would want to convert that back to radians before plugging that in. But now we can start to design for GC of 0. So if we're focusing on the magnitude response here, this is blown up here, you can kind of see, and we have our flat response, T0 times GC of 0. Excuse me. Second order system starts to cut in here. Here we have our phase boost, or the compensator kicking in, so now we have a decrease here of minus 20 dB per decade. Make sure you can kind of see how some of these, the magnitude gain values are here. This would be, you can combine that, here. I actually printed out the Bodie plot, might as well use it. So you can light, there we go. You can see here again, this was our second order system. We have our A and then our A over omega 0 over omega. So omega 0 is the value found from our transfer function. Omega would be the specific frequency that we're describing here. Oh, thank you. You guys let me go for 40 minutes.
Extra credit.
Well, thank you for pointing that out. I'm staring at this screen, so I'm not even looking over there. But just referencing back to this, like I said, this will be given to you guys, but realizing that second order systems kicked in here. Pop back over. And then at this frequency range, we're looking at T0, G0, F of 0. This is where instead of having this whole thing squared, we have to factor in the F of Z, F. And then here, once we've reached this past F of P, again, this is our A value as shown on the Bodie plot summary. But then it's F of P over F of Z times that squared, because these have to be factored in still. And, oh, I don't have these slides memorized, but every time I'm covering something, I'm finding the next slide has what I was trying to get at. But if we're looking at our magnitude response, this is a quick review of what we covered, feels like weeks ago. So given a magnitude A, this is our T0, G of C0. The frequency of the magnitude expression for the line slope at minus 20 dB per decade is A times F of A over the actual frequency that we have. For minus 40 dB per decade, it would be squared here. So, again, we're looking to find GC0. So at F of Z, the magnitude is F of C over F of C. Trying to get back to this there. But that's only in that minus 20 dB per decade range. If we're in the second order, so we're at F of Z, the magnitude is actually the T0, G0, F of Z. I need to find better words for these. F of 0 over F of Z squared. So we, at least in this case, we have T0 given to us already. We have F of Z that we calculated, and we have F0. So equating those two magnitudes, make sure so we know F of 0 is 1 kilohertz. We know F of C, because we set that to 5 kilohertz. So we equated the two expressions for at F of Z, given by this 20 dB per decade magnitude and the minus 40 dB per decade magnitude. Putting those together, at F of Z, T0, G0, this equation would equal F of C over F of Z. We can isolate by pulling out T0, 1 over T0. We're putting the inverse of this square over here, which means we have T0 that was given at the start as 2.33 if I remember correctly. We know F of Z, we calculated that. F of 0 has already been given. We've set our new F of C, and here's F of Z again. So all quantities are known. We can now solve for the gain of our compensator. So plugging this all in, 2.33, 1.58 kilohertz squared, 5 kilohertz there, which all equates to 3.4 for the design of the gain of our compensator. Now we're getting a quick look at the actual MATLAB response. We have in gain margin infinite at infinite hertz. We've boosted up our phase margin though, which is nice. That's about 5.9 degrees at 5.33 or 35 kilohertz, which is slightly shifted from what we designed for, but still within that range of that 5 kilohertz. And it's also showing us a higher phase margin than what we approximated for. But it's also why it's so important to use multiple simulation programs to kind of see where your phase margin is. But also, the most important thing is testing, because that's where we actually find out what our real world circuit will behave like. But if we plug this into PEX, and I think he ended up using 15 volts instead of 10, when the input step change we still have a large non-zero steady state error. We want to get that steady state error as close to zero as possible. So at this point, we need a different compensator to try and null out that steady state error. We've gotten our phase boost, but we also want our steady state to be as close to zero as possible.
On the previous slide, could we have reduced the gain of that to move the crossover back?
Yes, which is kind of what we're gonna get. We could reduce that gain, but then we wouldn't have that same phase margin that we would have there. If we just set that gain, we could, let me see, I'm trying to think of mathematically how to describe that. Because this is the C0 of these specific conditions. Because that is the values, again, these are straight line approximations. But what we're actually gonna do with some of the other compensators is we're gonna be increasing it a bit at some of the lower frequencies and then flattening out and then dropping it back down again. So we're gonna get to that, but it is a good point. I mean, you could increase that a little bit, but then we are changing, I mean, if we change that, we won't change our f of 0. We would change where our cutoff is, but if we just increase the gain, we might miss our phase boost going on here.
But
Is
if you decrease it, wouldn't
If you decreased
Slide it
it,
back.
we would probably slide it back a little bit. I'm trying to think of how that would affect us also, though. Slide it back, then we're getting less gain there. That would accomplish the phase boost a bit. We might end up with too much phase there if we push it back too far.
Well, I guess too, maybe, I don't think the gain actually would affect it, because the cutoff won't change.
Yeah, the cutoff won't change, because that'll still, and then, well, you just spike up higher here. We would need a different Q value too. Which would increase that. I would have to think about that a little bit more, but it's an interesting idea just to reduce that gain. But I know we reduce that gain depending on how much we increase it. We could just try trial and error, playing around with it, and might be able to get something better. But we would still run into an issue of the steady state error being way off here. I mean, not way off, but right now we're at 15. We're at about 120, I'm just give or take, millivolts of solid state or steady state error, which, again, depending on what you're designing for, that might be acceptable. But right now, we're trying to improve on this as much as we can. Oh, sorry, that would be 120 millivolts, because this is times 10, so it's right now going from 15, or about 14.97 to 15,120. So still quite a bit of steady state error. So we're gonna move to a new compensator design, the dominant pole with the lead compensation. So given this magnitude response, it's kind of what we're looking for here. What is the transfer function? So we have at low frequency asymptote is that the low frequency asymptote is that of a pole at 0 where the magnitude at f of a is a. So we have an integrator here, and then if we follow that by 0 at f of a, so we kind of make this omega a, if that matches up with this, then we would create a 0 there. So now we're gonna look at, I'm glad he put this on one slide because it makes it so much better. So we're adding the low frequency compensation, given here, with the lead compensated system that we already partially designed for. So we still have our f of c, f of p out here somewhere, but we're adding in the low frequency compensation. So combining these two, if we set the f of a the same as our f of 0, or sorry, we should be setting f of a to less than f of 0, or equal to, depending on how much we want to set this. We can adjust A to match the low frequency magnitude of T0, G0 of the lead compensator. This, again, just putting these two together, this kind of makes sense how adding one to the other, if we make f of A greater than f of 0, we would lose this flattening here. So we would have f of A over here. We'd end up with minus 60 dB per decade for a little while those crossed over, and would even out to minus 40 dB per decade, which doesn't really help us in this case. But we could set f of A to f of 0 if we're doing this dominant pole here. So now we have our dominant pole with lead compensator transfer function. So now we need to determine where omega I is going to be. So our compensated loop gain given here, we're plugging this back into our compensating system with our uncompensated system. And at omega A, the magnitude of the compensated system is given by this value. So we have omega I over omega A times T0, with omega A being less than omega Z, less than omega P, and less than omega 0. This should equal the low frequency gain of the lead compensated loop gain. So we want to set these values. So we have omega I and omega A times T0 equal to T0 G0 of the lead system. And we can delete out our T0s or divide them out. That removes that. Moving omega A to the lead compensator design, we end up with omega I equal to omega A, G sub 0, G to the compensator wording. So now we have omega I equals omega A over the lead compensator. How do we choose this, the frequency f sub A? So we want f of A to be less than f of 0, and f of A to be less than f of C over 10, so as the maximum phase lead at f of 0, so as to maximize the phase lead at f of 0 from the 0 at f of A. Now there's disadvantages to making that f of A too low. We want it to be lower than both of these, but there are disadvantages to making it too low. I think that comes up in like 3 or 4 more slides, not actually just the next one. So we have just our compensator transfer function described again. We have 4 parameters that need to be determined. We have still the omega Z, omega P that we described previously. We'll have the omega A and the omega I. So our design of the dominant pole with the lead compensator is now complete? No. The design is complete, we still have to choose an omega A, which also changes the value of omega I. We have omega Z and omega P can stay as they were previously. So, the phase response of this lead compensated loop gain combined with the low frequency compensation with f of A equal to f of C over 10. I believe we set f of C to 5 kilohertz, so that would make that 500 hertz. Put it, sure, is this one actually showing that? No. F of A is denoted as, oh, there we go, as f of 1 in this figure. So, f of 1, I look this over, it's being weird. Equals 10, f of 1, oh, I guess it's just showing here that it's, there we go. F of 1 over 10. Where's f of 1? Oh, that would be right about here. It's not actually denoted on here. But f of 1 over 10 is the set point that we have, we want to describe in our, if we're drawing this out individually. And then 10 f of 1 would be our crossover frequency. I think we get into this a little bit better when we blow it up. So we have our asymptotic Bode plot for the compensated loop gain, where f of A equals fc over 10, which is f of 1 here. Okay, now we actually show it. And here we have them, again, combined. So we have a value of T0, f of 1 over f. Just a little fuzzy there. Up until we hit that frequency f1. Then between f1 and f0, we have a flat gain response. And then we start, well, I'm not going to worry about this because this is all what we covered in the previous section. What's important here is what we have going on before all that. And here we can see that we get a nice bump up here from that 45 log, and then from here to here, we're actually increasing 90 degrees per decade. And during that, with that dominant pole added in there, we're actually bumping up above the minus 90 here. And then everything beyond that is pretty much staying the same. So it's right in this section between f of 1 over 10 and f of z over 10 that we have a change in our frequency response here. And here you can see the actual, well, not the actual, the MATLAB response to this dominant pole with lead compensator. So you can see we're starting up a lot higher here, decreasing down, we flatten out right around 500, and hard to read it off of there. Flattening out, then we hit our 1 kilohertz, and we have the same kind of response going on the back end there. And we've actually reduced our phase margin just a little bit, about 5 degrees, in comparison to just the lead compensator. Here we can see our response to a input voltage change. You can see we jump up, then we get pretty close to returning to a steady state. We have a settling time of about 1 millisecond, which is not bad. So the phase response, now what we're doing here is this is where, get back to it. I don't know why we didn't start with the bad one before we get to a good one. We're going to show in these next few slides where there's the disadvantage to making the f of a too low. So in this case, what we did was we are looking at the phase response of the lead compensated loop gain combined with a low frequency compensation with, now f of a is a 33rd instead of a 10th of the corner or crossover frequency. You want to say corner. Note, f of a is still denoted as f1 in the figure along the side. It's pretty much the same, only we have actually decreased f of 1 much lower. So we had it at 5 kilohertz divided by 33. I'm not going to try and do that. It's 150 something hertz. I wonder if it'll show it. No, it doesn't have it calculated. But you can see here the difference being now that we've reduced this f of a to a much lower value, we're kicking in this phase boost much earlier. Or not phase boost, I don't want to call it a phase boost, but an increasing phase at a much lower value, and that allows it to increase more. We would get a little bit more phase margin, which might be good, but there's also some drawbacks that we'll get into here. Getting back to this, where we're actually combining and blowing up some of these plots, makes it a lot easier to see. So we have the asymptotic Bode plot with f of c at 1/33 of the corner frequency. I keep saying that. Crossover frequency. F of 0 is the corner frequency. So our magnitude plot up until f of 1, we still have T0, f of 0 over f, which would be decreasing. We have a much wider range here where we have a flat gain, and then nothing really changes beyond here. Does that make sense? I keep saying nothing changes there, but everybody understand why I'm kind of crossing over this. We design beyond that, we're only worried about what we're changing with this lead compensator. But getting back to our phase diagram, phase plot. So we have here, we're at minus 90, and then here we're increasing because of that lead, the dominant pole with lead compensator. And we're increasing a lot more over this phase boost, and then we're not quite hitting minus 90 there, but then we're looking pretty good here. This looks pretty good offhand. It looks like we're probably gonna have a higher phase margin. Overall, that's looking pretty good. We can look at it again here with the actual Bodie plots using MATLAB. And we see, again, infinite gain margin, phase margin. We've bumped back up about 4 degrees, I believe. It was at 50.5 with just our previous design. So, hey, it's looking pretty good. But when we look at the input voltage change, what we've actually changed there is the settling time of our system. So we're kind of adjusting the, I don't know if I remember correctly, our damping ratio to create a longer settling time for the system. Depending on, again, what you're designing for, that longer settling time might be acceptable. For looking at this over right now, we'd like a shorter settling time. We're trying to reduce a lot of these values. So we would say that first design where we're keeping f of a to 1/10 of the crossover frequency would be better. Is that kind of, is this making sense? We're kind of getting to the end of what the actual design sections. We didn't really cover just the proportional or some of the other minor ones, but.
So the dominant pole, the reason we're designing for that is to have better steady state error,
Yeah, the dominant pole, yes.
and then the lead compensations for the phase margin.
For the phase margin, also the lead compensator helps with the steady state error, and sorry, I'm make sure I don't mix these up because I'm going to very often do that. Lead compensator improves the steady state error. No, dominant pole fixes the steady state error. Lead compensator. No. Oh man, I have these mixed up. I know I'm saying them wrong.
Lead compensators improving the phase
Margin. Let me see. The dominant pole helps with the steady state error. Jeez. Yes, because that adds that 0 in there, which helps our steady state error get reduce. And I mean, even on here, I mean, you can't really tell because it's PEX. There's still a slight steady state error. It's much improved over that, I believe, 120 millivolts that was available with just the lead compensator. But, okay, yeah. Looking closely at the design of these two components, compensators, so the lead and the dominant pole with lead. The derived formulas need to design, not just used available. It just sounds weird. Derived. Oh, we derive the formulas needed to design, not just used available formulas. The lead compensator will extend the bandwidth while boosting the phase, which could result in a quick response with a good phase margin, minimal overshoot. The dominant pole with lead compensator has the properties of the lead compensator together with a integrator, which provides that 0 steady state error. I guess this kind of wrapped up what I was trying to say there just a moment ago. Okay, questions on that before we take a quick 5-minute break? I feel pretty good. This is pretty much what you will be using for the Lab 6. Like I said, I will lead you guys to where some of these formulas will be and guide you a little bit more on which values to set, because I might have mentioned previously in Dr. Tymersky's book, a lot of us assumed, and I know when I was the TA for this previously too, a lot of people assumed when he used C1, that's the one you should set. And I believe, if I remember correctly, you probably want to set C3, the third capacitor, and then do your calculations from there. But I'll describe that more in the actual write-up for Lab 6 when I post that this weekend. Let's go take a 5-minute break.